a few tutorial questions for calculating the friction inside the pipe. All right. Now, there are two types of flow analysis, especially deal with the heat loss. So we have two types. So in the coming test 2 and your final exam, you need to calculate these two heat loss or friction loss inside the pipe. So HL equal to major plus minor means you need to calculate the major losses that contribute by the viscous effect in a straight pipe, meaning major losses majorly from the fluid itself, maybe from the water, from the mercury, from the fluid itself, okay, from the content itself. Then after that, you need to plus calculating the heat loss for minor. Minor means those component in a pipe, for example, the T junction, the 90-degree bend, anchor, and all this, right? So you need to calculate these two effects. Okay, so quite straightforward. So if you're asked to calculate the overall heat loss, make sure you're calculating major loss and minor loss. Some question will ask you to ignore minor loss. So make sure you know how to differentiate between major and minor. Major is on the fluid itself. However, for minor loss, you have a T junction, the elbow, and all this. Then you need to calculate for minor loss. Okay, so let's see. We look at major loss first. So major loss, it will, we learned about the drop of pressure previously. The delta P and the wall shear stress. So we learned about the parameter previously, delta P, HL, and wall shear stress. So just to recap, you can calculate the shear stress in a function of density. And the rest you can read from the screen here. So this is from the dimensionless analysis that you did in your 3179. Okay, so delta P equal to function of velocity, diameter, length, the condition of the surface, and the dynamic viscosity of the pipe here. Okay, I want you to show you one important solution. So if you're calculating for turbulent flow, then there will be a sublayer viscosity happening. But anyway, this one will not be in your test. You just need to strengthen your understanding in fluid dynamics or fluid mechanics. As you can see, the line, this diagram over here, the roughness of the surface will give you different condition, right? This is a self-explanatory. If you have a rough wall surface, then you'll see the flow is actually having some turbulent flow or roughness, rough flow along the surface. However, if you have a smooth wall, then yes, you have a little bit of disturbance, but not much compared to the rough wall here. Okay, so okay, this one you can read. I want you to cut you through. This is the slides here is more on the dimensionless analysis. This one is the last chapter of 3179. So you can read through the slides just to recap back what is dimensionless analysis. So I will not cover all this. So you need to read my slides just to recall, right? What is important is that when you learn about your 3179, something called F friction factor given by this equation, or most of the time we will write delta P equal to F L divided by D 1/2 rho V squared. This is dynamic viscosity. This one is called dynamic. Apologize for my writing. Dynamic pressure. Sorry, dynamic pressure. Okay. So remember this important equation for flow analysis. Okay, this one. So delta P, the drop of pressure between 2 points. Let's say you have a pipe between 2 points. And again, try to differentiate pipe flow and channel flow. Open channel flow is different. Pipe flow between point 1 and point 2. If you want the flow to flow, there must be a changes of pressure. Point 1 must be higher than point 2. So that P1 must higher than P2 so that the volume flow rate can flow from point 1 to point 2. And to calculate the drop of pressure between these 2 points, you use this equation, delta P equal to FL/D times your dynamic pressure, half rho V squared. I think this one, you've seen this one before in your 3179 last chapter. Okay. And remember, when you have a laminar flow, you can straight away use 64 divided by Reynolds number. This one in the previous slides, you can see. Okay. All right. Now, this is an important equation for today. When we talk about major losses, and you're having a steady incompressible flow with no shaft work head, then mechanical energy you can write in this form. We cover about this equation when we talk about nervous stroke equation. I think last lecture. All right. So we're having this form of energy equation. So again, what we assume for this equation, we will have constant diameter. D will be the same. So when your D is same, meaning your pipe diameter is same, and is incompressible steady flow, meaning 0.1, your V1 will be the same as V2. Your horizontal pipe, meaning if you reference axis at the center, again for pipe, we always refer to the center of the pipe where you will see reference axis X, while for your Y, we will use R as your reference axis. Okay, always refer to the center when you look at pipe flow. We have a fully developed flow, so alpha 1 will equal to alpha 2. So by looking at the assumption, these three assumptions, cancel Z1, because Z1 equal to Z2, you move Z2 to left hand side or move Z1 to right hand side, you will cancel each other. Then because of alpha 1 equal to alpha 2, V1 equal to V2, you can cancel this one. So the rest is just rearranging of this equation. You will be having delta of P will equal to P1 minus P2 will equal to specific gravity times HL. Okay. When you solve question for chapter 3, write this equation, write this assumption. Okay, write this equation. After that, write this assumption. This one, 1 mark, 1, 2, 3, 3 mark for assumption. Conclude your delta P, how you calculate delta P will be 1 to 2 mark. Okay, pull this equation when you need to solve major loss question or your coming test 2. Write this equation, write your assumption, check whether the question mentioned this one or not. If the question mentioned this one, write the assumption, rearrange the equation based on your assumption, arrive at one individual equation, delta P equal to P1 minus P2, gamma or specific gravity, HL. Okay. Today, this is our focus, which is our head loss. Okay. And we are under major head loss. Okay. We have two H. HL, we have two. We have two dimension we need to, or two component we need to analyze. One is major. One is minor. Okay. Every time you have a pipe flow, when there's a fluid flowing into the pipe, they will always have major head loss. However, if this pipe connected to an elbow, here one elbow, second elbow. So you want to calculate the head loss at this corner, you need to include minor. Okay, minor. Minor is those component in the pipe. Or you have a valve, you have an opener for the flow to flow in, then this one also included this component. Okay, HL major, or this one, major losses is concerning the flow inside the straight pipe. Okay, this is more on the fluid itself. Fluid and the reaction with the pipe is the major. Then the minor will be the component. Clear on the differences between major and minor? Clear? I'm going to ask the question. Do you know how to differentiate major and minor? Okay. Ask me question now if I'm not clear. I'm going to ask question after 10 more seconds. I'm going to ask question about minor and major. Anything you're not sure? I'm going to ask question. Ask me now. If you're not sure what is major, what is minor, ask me now. Okay. By looking at these slides, I'm going to ask question. This question will go to Raj. Raj, let's say you're having a pipe, and this pipe was connected to a valve. This valve will allow the flow to flow or stop the flow. Okay, the flow is flowing from the left to right. You have point 1, point 2. So this is your Q. So Roger, how do you calculate major heat loss? What you need to consider when you want to calculate major heat loss? Raj, are you there?
Yes, sir. Yes, sir. Wait as well.
Raj, do you understand the wording on the slides or not?
Yes, sir.
Yeah.
So it should be calculated because it's straight pipe. So of course it's major loss.
Mhm.
Then mm,
Do
we
you
need
calculate?
to take the
Yeah.
pressure first.
Yeah. Do you consider this valve or not for
Um,
major losses?
yeah, sir. So
Major loss consider it means your major loss consider this component.
no, sir. I just include the pressure in front first because we no need to consider the valve.
Mm,
So we need to consider about the in and out only. I think.
okay. Yeah, your answer is
Uh,
okay, is only. All right,
uh,
so I'm going to highlight what is the major head loss section that you need to consider here and here. This one, the orange color one, is you need to calculate HL major. It's the area that you need to focus to calculate the head loss. Why? Because it's focusing on the straight pipe and the viscous effect. What I mean by viscous effect? It means that if the flow is flowing through a straight pipe, you're going to get this profile, 0 at the wall, velocity 0 at the wall, Vmax at the center, and you're considering the pipe condition, the straight pipe condition, which means the roughness of the pipe, the friction at the surface of the pipe only. Okay, this is major. However, for minor, make sure you get this idea, you understand this idea, then you have no problem solving the major minor question. So for HL minor, it's more on the component. So for example, this diagram here, this is the component that used to stop or to channel the flow from left to right. So minor HL only consider on this component only. Okay, so the total head loss means you need to add the yellow color plus the blue color. This is the head loss. Okay, the head loss. Okay, what is the idea of head loss in the layman term? It means if you have a pipe and you measure, you put in a capillary, all right, you put in a capillary, and let's say this is your valve. Okay, and you channel the flow from left to right, Q. So as you have water, there will be a height of water here. For example, H1 at station 1. Then you measure the second station. Then you measure the third station. Okay, so as the flow past this component, there will be a drop of height. A little bit, drop a little bit because it's just minor. It's a component, so very, very small losses. Okay. Then after that, of course it can be big lah, but normally it's a small changes because usually the valve and all this, the internal is smooth surface. Okay. And then after it reach a certain distance, it will further drop down H3. So you can see the height of the water is dropping. So we are calculating what is the losses inside the pipe using the height of the water capillary here. Okay, yeah, so I hope by this graphic you can get some idea what is head loss. Right, head loss actually you're calculating the drop of the water, the drop of the pressure inside the pipe. Okay, so let's jump to the equation. Okay, remember this equation. HL equal to FL d V squared over 2G, because we already proved that delta P equal to FL divided by D and the dynamic pressure half rho V squared. You substitute this one inside here. You equal both sides. You rearrange the equation. You get this equation. Okay, delta P equal to this one. You put inside the mechanical energy that you derived just now. You rearrange the equation. You will get HL equal to FL divided by D, V squared divided by 2G. And then the specific weight is given. Specific is equal to density times gravity. So it means that delta P equal to rho GH. You familiar with this one? Rho GH, hydrostatic pressure that you learned in your Bernoulli equation. Rho GH. So rho G actually is this one. Okay. Okay, so this chapter actually combining what you learned in the other module, you combine in this chapter. One equation, important equation for you today, with these slides. This one, energy equation. Again, write this equation, read the question of the test or final exam, write this assumption, each one give you some marks, rearrange, apply this assumption into the energy equation. You will get this one. You get this one. After this one, recall what is delta P equation in terms of friction, length, diameter, density, and velocity of the fluid. Substitute inside there, rearrange, you get HL equal FL divided by D, V squared divided by 2G. Okay. Recall, okay, so this one, there's a name for it. We call it Darcy Weisbach equation or Darcy equation. It is super important in chapter 3. Darcy equation is very important for chapter 3. This one, you write somewhere in your answer, will cost you 1 to 2 marks. Okay, when you need to find head loss, especially for major head loss. Okay, again, today, print this, try to memorize or try to identify this equation somewhere in your notes or in your memory. HL equal F friction L over D V squared divided by 2G. By all means, go and memorize this one. This one is to calculate major losses, which is only in straight pipe. We take into the effect of the viscous of the pipe, the condition of the pipe, and the fluid only in the long pipe. Do not include component, example, the valve or 90-degree elbow. Okay. Do not include these two, only in pipe. So this one is important. This is called Darcy equation. Or sometimes it will help you to solve some, to score some marks. We will mention apply Darcy equation in your analysis, meaning straight away you need to write this one in your answer. Okay, we just want to see whether you understand what is Darcy equation. So this one, if you see this one straight away, write this equation. If you see Darcy Weisbach equation in the question itself, then straight away write HL equal to FL divided by D V squared over 2G is a Darcy equation. You'll score 1 to 2 marks for showing your understanding what is Darcy equation. All right. Again, this is an important statement. Darcy equation, or HL equal to FL divided by dV squared over 2G, apply or valid for fully developed. Again, we already explained what is fully developed. Since the first lecture of this chapter, I show you the pipe, right? The pipe system, how fully developed region is about. So go and read or go and listen back to the previous lecture. Steady, incompressible pipe flow. And it doesn't care the orientation, whether it's a horizontal or on the hill. Meaning it doesn't care the pipe is this way, this way, this way, or this way. It doesn't care. Okay. Important equation, huh? So again, just a reminder, this delta P equation, when you want to use Darcy Weisbach equation, remember when you want to find the delta P, just need to take note, this equation only apply for horizontal pipe. If you have a tilted pipe, then you need to use this one. You need to use information from these slides. Still remember these slides? I ask you to memorize this one. These slides on the left hand side is horizontal. Left hand side with the angle, and the theta is positive anticlockwise. So when it's uphill, downhill, your sine theta going to positive, negative. So read something on the slides here. Okay. So try to recall these slides when you solve pipe problem, whether it's horizontal or slanted. Okay. Go back to our lecture just now. So again, be careful calculating delta P. This equation, delta P equal to FL divided by D half rho V square, only for horizontal pipe. If it's slanted, then you need to refer to the right-hand side of the screen just now. However, for HL it apply for all condition. Darcy Weisbach equation do not influence by orientation of the pipe. However, delta P, yes. Okay, be careful using these two equations. So this is how you summarize your equation. So if you have a straight pipe, then V1 equal to V2. You have an incompressible, alpha 1 equal to alpha 2. So take out these two terms. Then you times the specific weight in both sides of the equation, means this gamma, you times gamma, all of the terms on the left hand side, and also times gamma, all term on the right hand side. So you'll get P1 plus gamma Z1 plus P2 plus gamma Z1 plus gamma H2. Then you want to find the change of pressure inside the pipe. So what you do, you pull your P2 to the left, you put this one to the right. You rearrange the equation, you'll get this form. And the next one, we substitute your HL by Darcy Weisbach equation. I highlight in the box on the screen. You substitute the Darcy-Weber equation inside here. Okay. You get this form. And let's see. I have one question for one of you. Dinesh, what is this one? Dinesh, are you there? Dinesh? Dinesh, are you there? Dinesh, are you in the class? This is a recorded video. Okay, Dinesh is logging out from the class. Raj, are you there?
Yes, sir.
Okay, Raj, one simple question. What do you understand about this one? What is this gamma?
Sir, sorry, sir. Can you tell again? What
What is this? What is this? What is this term? What is this?
Rho equals to EGH, sir. P equals to EGH. Rho GH. Sorry. Rho GH.
I'm asking you about this one. I'm not asking you the HL. I'm asking you about this one. What is this in this equation? What is this? What do you understand about? What is this?
Sir, can you hear me, sir?
Yeah, I can hear you, Dinesh. What happened?
Sir, I got disconnected, sir. Sorry, sir.
Okay, all right.
Sir, I think the change in pressure, sir.
I ask one more time. I ask you to pay attention to the screen. The answer is on the screen. I'm not sure whether you're in the class or not. I'm asking you what it is. What is this gamma?
Sir, is that P1 minus P2? You're asking the equation or what you're asking, sir?
I'm asking you what is this thing? What is this? What is this gamma?
What is
What is
this?
this? What is this? I'm not asking you about P1, P2. I'm asking about what is this? What is this thing? Yeah.
Sorry, sir. I don't know, sir.
You don't know. Are you seeing the same screen here?
Yes, sir.
Okay.
But what I know is the one is pressure, right, sir?
Okay. I just give you a hint. The answer is on the screen.
Answer is on the screen.
Yeah.
Sir, is that steady incompressible flow?
Dinesh, just now I asked you the same question. What is this? What is this gamma?
The flow, sir, incompressible flow.
No.
So specific weight is
So what is the answer?
specific weight. Sir.
This one is specific weight. The answer is on the screen.
Oh.
Okay. This specific weight, specific weight equal to rho g. Dinesh, do you understand how to get this one? What
Yes,
is the
sir.
differences between the red box on the right and the red box on the left? What is the difference? Do you understand what have we taken out from the equation? And what have we added to the equation?
G, sir.
What
We
happened
take
to the G?
We take out the G.
You take out the G from where? How you able to take out the G? Can you explain? Can you explain? I know this one boring for Shirley. Shirley, patient a bit. Are you able to explain how you get from here to here? Can you explain? How you get FL over D rho V squared 2? Can you explain, Dinesh?
Because the gamma have G, sir.
Gamma is G.
Yeah.
Raj, what is gamma? Raj, are you there?
Yes, sir.
What is gamma?
So the gamma is
Just now you answer,
yeah,
right?
the
What is
pressure,
gamma?
the rho GH. The gamma
Rho.
equals to
Gamma equal to what?
P equals to rho GH.
I'm not asking you the P. I'm asking you the gamma. What is gamma?
PG, sir.
Huh?
PG.
Okay, I'm going to repeat this one from the beginning. Since you want to drag the class, I can drag. You're seeing P here. This is P to you. This is P. Is it the same?
Rho G, rho G.
Raj, do you see this one as P?
Yes, sir. Yes, sir.
What is this? What is rho? What is the gamma?
Rho G, sir. PG, sir. PG.
You're seeing PG.
Yes, sir. Correct.
Repeat one more time. Specific weight equal to rho G. Specific weight equal to rho G. Do you hear it, Raj?
Sorry, sir. Yes, sir.
Dinesh, can you explain how you get from rho gamma HL to this equation? Can you explain? Surely later you explain to the class how you get gamma HL to FL over D rho V squared divided by 2 if your friend not able to answer. This is mathematic question. It's nothing deal with fluid mechanics itself. If you're not able to answer this one, I'm going to ask your advanced mathematics teacher or lecturer drag you back to the advanced mathematics or calculus mathematics 2 class to retake the class. It's just substitution. You're not able to do substitution.
So we just substitute the rho in HL and then we cancel out the same thing, right, sir?
Yeah. Correct, Raj. I'm asking the same question to Dinesh, but Dinesh seems not able to answer. Dinesh, this question is for you. How to change this to this whole thing? Are you able to see it, Dinesh?
Yes, sir.
Explain.
Just substitute, sir.
Yeah, substitute. Okay, explain to me what is gamma.
It's rho G.
Rho G. What is HL?
The equation, sir.
Which one?
FL. The one you got V2 over 2G.
This one, right?
Yeah.
All right. So I think Shirley don't have the opportunity to answer. You just substitute the equation here into here. All right, then you can find the drop of the pressure inside pipe under major head loss effect in here. Under major effect. HL major. Later section, you will have another additional HL minor. In this case, we will only consider major. Okay. Next one, this table is under the graph that I asked you to download from Moodle just now. It is inside the, you need to download this one, huh? Moody Chart. This one. I ask you to download before our start our class. So I extract this table from this Moody Chart. It's an important table for your test and final exam. So this table, 8.1, is the roughness, equivalent roughness, will give you this symbol. Roughness, in this table, you have imperial unit and you have unit SI. In the test, don't read left-hand side because we are using unit SI. Focus on this side. Okay, so if the exam mention using rivet steel, you use either within this range. If the exam using cast iron, you use 0.26 for equivalent roughness. If the question asks using draw tubing, you use 0.0015 for equivalent roughness. This term. Okay, so if the question asks about plastic or glass, you use 0. In your answer, you write equivalent roughness, small e here, epsilon, 0, you will score 1 to 2 marks. Just this simple answer. Okay. Now, what is this deal with our major head loss? What's going to do with this equivalent roughness, or why do we need to study about this one? So, because this one will help us to calculate the parameter on the right hand side. If you look at the if you look at the Moody chart on your screen here, you have 3 axes. One, F, which is the friction loss. Bottom one is the Reynolds number, rho VD divided by mu. On the right hand side, you have equivalent roughness divided by D. You have F, rho, Reynolds number, 3 axes on the chart itself. So on this chart, you already have the Reynolds number equation. So there's no reason for you, sir, I don't know Reynolds number. I don't know how to calculate Reynolds number. You are sure seeing Reynolds number chart in the test or final exam. So no reason you don't know because Reynolds number is inside the chart unless you're not paying attention. So if you don't paying attention, you don't know or answer this kind of question, it means that you need to repeat this module again next semester. And again, I don't want you to repeat this module. But unless you still want to see me, then welcome lah. Okay. All right. So it's very easy to use this chart. So you have a few reasons in this chart. So as you can see here, I already show something on the screen here. If you're having a smooth surface, you just follow this line. Okay, smooth line. And if your flow is, you see this dashed line, right? Dashed line. So if your region fall below above this dashed line, it means you're having a turbulent flow inside this region. You're having a turbulent flow. If any point that fall within this region, it means that you're having a turbulent flow. If you're having a laminar flow, then you are following, in here is labeled for you already, meaning this region, most probably you will have laminar flow. You see this line, right? So here, you will have a different scenario, okay? Okay, we have clear on the Moody chart already. Moody chart, you have three axes: friction, load, friction factor, Reynolds number, equivalent roughness divided by D, and we can solve. All right. So how do we use this chart to solve question? So this is just a highlight notes. So this highlighted red region is for the laminar flow following 64 Reynolds number. So this one I think is 64 divided by Reynolds number. Okay. So turbulent flow and so on. So let's look at another presentation of Moody chart will be the same. It's only the colors and the lines is a little bit different. So if you look, compare side by side, Moody chart always have three axes. Friction factor on the left, Reynolds number on the bottom, and the relative roughness on the right hand side. In this case, this chart is using K as relative roughness. It's equivalent to the epsilon that you see in the previous chart. Same. All the line will be the same. But in exam, in test or exam, you need to download this chart beforehand to use this chart in your test or exam. Equation, if you have a non-laminar range, you will use Calabrooke equation, with given on the screen here. It means all this line, you see all this line here. You are using a logarithm equation to find. Again, you are looking at three parameter: F, friction factor, equivalent roughness, diameter of the pipe, Reynolds number, and the friction number. So this is the equation that you can solve. If you know you have four unknown there, as long as you have three unknown, you're able to solve another one. So they are F, epsilon, D, and Reynolds number. You know either three, you're able to solve one of them. Okay. Another equation used for major losses calculation is Hallen equation, with given by this one, also focusing on F, epsilon, D, Reynolds number. Both will give you similar answer. Okay, it's not same, but similar, very near number. So let's look at one example and then we call it a quick one, how to solve this one. So if you look at the statement, you are having a 4 mm diameter tubing with velocity of 50 meter per second. And then you need to calculate pressure drop at particular section, pressure drop at 0.1 meter section, if the flow is laminar, and then what happens if the flow is turbulent. Okay, I'm going to very fast on this example. So for standard temperature, we're using air. Air, the rho is 1.23 kilogram over meter cube, viscosity given by this value. So from here, first steps, always calculate Reynolds number, substitute the number, Reynolds number equal to rho Vd divided by mu. You substitute, you get Reynolds number 13700. Okay, 13700. This is a turbulent flow. Remember the magic number that we learned? 2100 and 4000. This number more than 4000. That's why turbulent flow. Okay, let's try to solve the first section. Is tell you if the laminar flow, what happened? So laminar flow, you use Darcy friction factor, F equal to 64 divided by RE. You already calculated the Reynolds number. You get the friction factor F equal to 0.00467.
Doctor.
Yes.
I'm sorry for cutting you out. Doctor, may I leave a bit early because I have presentations coming up, and my lecturer is calling us.
Okay. All right.
Okay.
So I think we end our session here. We will continue this one in next lecture. All right. See you guys in next lecture.
Thank you, sir.
Okay, thank you.
Sorry about that.